Okay, let's move on to number 17. And the key equation that you need to know for these problems around this is the terminal voltage, that which you actually realize from a battery is equal to the internal EMF of the battery, which is the total voltage in the battery minus the current times the internal resistance in the battery. So for this first problem, number 17, what is the terminal voltage of a large 1.54 volt carbon zinc dry cell in a physics laboratory to supply at 2 amps to current if the cell's internal resistance is 0.1 ohms? Okay, so if you plug those numbers, the terminal voltage for number 17 here, the terminal voltage will equal 1.54, which is the the EMF, times 2, which is the current, times 0.1, which is the internal resistance. You do the math here and you get 1.34 volts. So the terminal voltage is 1.34 volts. Now, what happens to that internal stuff? Well, what happens is that this voltage is what produces power, and it asks the question, what is the power? This is the total power that's produced, and this is the actual realized power. So the total power produced is going to be equal to this total available EMF times the current again, which is going to be 3.08 watts. But then the realized power from this battery is only going to be equal to the terminal voltage, 1.34 times 2, which is 2.68 watts. Now you notice the difference here is about 4.4 watts. Where does that go? Well, that's why batteries get hot, is because the internal resistance causes a loss of power, and that power, and we'll be doing some problems here in just a minute where we actually calculate that. Number 20, a car battery with a 12 volt EMF and an internal resistance of 0.05 ohms is being charged with a current of 60 amps. Note that in this process the battery is being charged. What is the potential difference across the terminals? Okay, so the potential difference across the terminals is another word for the terminal voltage. And so that is going to be, now in this case, it's interesting because what you have is you have the external adding instead of it being lost by the use of the battery. That's the point about saying it's being charged. And so you're going to have the voltage that they're asking for is actually going to be equal to the internal EMF plus, instead of minus, plus I times R. Okay? So that's going to be 12 volts plus 60 times 0.05, which ends up being 15.0 volts. Okay, the second question on number 20 is, at what rate is thermal energy being dissipated in the battery? Okay, so B is the power is equal to I squared times R. Now this is the same as saying V times I, because V is equal to IR, so that's where I squared comes from. And in this, it's going to be 60 squared, because that's the current, and the internal resistance is 0.05. And so you're consuming or producing 180 watts internally of power, okay? And that is converted into thermal energy. At what rate is electric energy being converted into chemical energy? Okay, that's the part that's actually being used to produce the voltage. And so in that case, you use I times V, which is 60, and it's a 12-volt battery. And so then that you subtract from that the internal watts that is being dissipated by the battery internally, and so what's left is 540 watts. So this is the total power that's being supplied. 180 of it goes into the internal dissipation of the battery, and the rest goes to converting the battery's chemicals so that it can produce power in the future. And then the last question is, what are answers A and B when the battery used to supply 60 amps to a starter motor? So they're asking you these questions. Instead of it being charging, it's now using to supply. Okay, so your first one is the terminal voltage. Now we're back to minus here. So it's going to be 12 minus 60 times 0.05, or 9 volts, is actually supplied. Okay, the power actually ends up being 60 times 0.05, or 180 watts. $60 squared, excuse me. Okie doke. Number 22. A label on a portable battery recommends the use of rechargeable nickel-cadmium or NiCad batteries, although they have an EMF of 1.25, while the alkalines have an EMF of 1.58. The radio has a 3.2 resistance. Draw a circuit diagram of the radio and its batteries. Now calculate the power delivered to the radio. Okay, so first thing you do is you draw a picture of the circuit, and it looks something like this. Here's the radio and here's the battery. Okay, the power delivered is equal to, well, first of all, it's easiest to start out by saying, using the nickel-cad batteries, you have a current that's equal to E over R plus R. So that's going to be 1.25 for the nickel-cadmium and 3.2 plus 0.04 for the internal resistance. And if you add those together, you get 0.384 amps. And then the power for this is now going to be I squared times R, which is equal to 0.384 squared times 3.2. And so the radio power usage is 0.476 watts. When using alkaline batteries, now we do the same calculation using alkaline batteries. So this is using the nickel-cad batteries. Now let's use the alkaline batteries. Now the alkaline batteries are a little bit different. It's the same calculation, but now E is 1.58 instead of 1.2, and this is 3.2 still. That's the same. But now the internal resistance is a little higher, and so you end up with overall a higher current. And you also, when you calculate the power using this same formula, you're going to have a higher power usage with this situation. And the higher power usage ends up being 0.691. And the question here is, the last question is, does this difference seem significant considering the effective resistance is lowered when you turn the radio up? The answer to that is if this resistance decreases, then the difference between these two decrease. And so I would say no, that it's not significant. Number 28. Number 28 states, a 12-volt EMF battery has a terminal voltage of 16 volts when being charged by a current of 10 amps. What is the battery's internal resistance? Okay, it's similar to the previous problem we had, problem number 20, where we have to use the plus instead of the minus because it's being charged. So the V is equal to E plus IR. And what we want to know is R. So if we solve this equation for R, we get V minus E over I. So we have 16 minus 12 over 10. And the answer is going to be 0.4 ohms of internal resistance. Number 28b states, what is the power dissipated inside the battery? All right, the power inside the battery dissipated is going to equal I squared R, which is equal to 10 squared times 0.4. So that's going to be equal to 40 watts. That's 10 squared is 100 times 0.4 is 40. C says, how much does this battery heat up? It says, at what rate will the temperature increase if the mass of the battery is 20 kilograms and the specific heat is 0.3 kilocalories per kilogram? Okay, so we have Q is equal to MC delta T, and what we want to know is delta T. So we say delta T is equal to Q over MC. And Q is 40 joules per second, okay? M is 20 kilograms, and C is 0.3 kilocalories per kilogram degrees centigrade. Now we have to convert kilocalories to joules, because this is in joules, and that's 4.19 joules per calorie, or 4.19 kilojoules per kilocalorie. So we can either change this to kilojoules or change this and this. So let's leave this the way it is, and we'll change this number to kilojoules. So that's going to turn into 0.040 kilojoules per second, okay? And if we do all the math here, we end up with 0.00159 degrees per second, or 0.0956 degrees per minute. And as I said, I'd do a problem where it looked like where I showed you what happened with the heat, or what happens to a battery with the heat. Okay, let's stop at this point and we'll go to the next part.